Hi, this is Dr. Barrett Givens from Cal Poly Pomona, and this video is to demonstrate a few homework problems for my Math 310 students. The first problem is, for n greater than or equal to 4, prove that n factorial is greater than 2 to the n. I'll start with a little bit of scratch work, so I like to start by just trying some numeric values, just some examples to see if it works. So when n is 4, n factorial is 24, and 2 to the n is 16, and 24 is greater than 16. Also, when n is 5, I get 120, which is certainly greater than 32. Okay, so that sort of checks out. Now let's think about our inductive hypothesis. So for our inductive hypothesis, we would assume that n factorial is greater than 2 to the n. You could say k factorial is greater than 2 to the k, or m factorial is greater than 2 to the m. It's a dummy variable, so whatever variable you want. Now I'm going to want to prove the same statement but with n plus 1 instead of with n. So I'll start with the left-hand side with n plus 1 factorial. And using a well-known property of factorials, I can rewrite it that way. Now I'm aiming to show that this is greater than 2 to the n plus 1. 2 to the n plus 1. So I want to use my inductive hypothesis here because I have an n factorial. N factorial is greater than 2 to the n, so I can make that substitution, and it's greater than. Now, what do I do with that n plus 1? Well, I'm aiming for 2 to the n plus 1, which is 2 times 2 to the n, so I want to get rid of that n plus 1 somehow. And notice that since n is greater than or equal to 4, n plus 1 is greater than or equal to 5. So I can make that substitution. Now, I don't want 5 times 2 to the n, I want 2 times 2 to the n. But luckily these things don't have to be equal, it just has to be greater than, and 5 is greater than 2, so that's fine. So I can say 5 times 2 to the n is greater than 2 times 2 to the n, but 2 times 2 to the n is exactly what I want. And so, yay, I'm happy. Okay? Now, when I write out my base case, a couple things I want to point out. When I write out my base case, for example here, I'm going to want to say that n factorial is greater than 2 to the n when n equals 4. So what I'm going to do is I'm going to write these going this way, n factorial equals 4 factorial equals 24, and then I'm going to say, well, 24 is greater than 16, and then write these going back that way. And that way I end up with a long chain that starts with n factorial and ends with 2 to the n. Okay, so let's see how that works. Okay, so now I'm going to start my formal proof. First I have the base case, and as I said, I'm going to start with the n factorial side. N factorial equals 4 factorial equals 24. And then I'm going to write the 2 to the n side sort of in reverse order, so I'll say 24 is greater than 16, which equals 2 to the 4, which is 2 to the n. So if you notice here, I have n factorial equals equals greater equals equals 2 to the n. So altogether I have n factorial greater than 2 to the n. Okay. Now I'll start my inductive step. I'll let n be greater than or equal to 4, and I will assume, because it's my inductive hypothesis, it's something that I'm assuming, I will assume that n factorial is greater than 2 to the n. I shouldn't say then n factorial is greater than 2 to the n, because that makes it sound like I already know it. It's just something I'm assuming at this point. Okay, now remember that we're going to use the fact that n plus 1 is greater than or equal to 5, and so it would be really smart to make a little note of that here so that when it comes up in the proof, the reader is like, oh yeah, you mentioned that, that seems fine. Okay, so now that we've kind of primed everything, we'll start with n plus 1 factorial, which is n plus 1 times n factorial. Now n plus 1, because of my note, it's really clear that n plus 1 is greater than or equal to 5, and because of the inductive hypothesis, n factorial is greater than 2 to the n, and so I can do both substitutions at once here and get 5 times 2 to the n, which is greater than 2 times 2 to the n, which is equal to 2 to the n plus 1. Great, and that's exactly what we wanted, so we've completed our inductive step, and we can say, therefore, by induction, n factorial is greater than 2 to the n for any n greater than or equal to 4. Now for the second problem, we're going to prove that the limit as x goes to infinity of x to the n over e to the x equals 0 for n in the natural numbers. And as part of the instructions, it says use induction. Now, some of you proved this without using induction, but I didn't give you very many points for that because the instructions did say to use induction. Okay, so sorry. All right, here comes the proof. Proof by induction. As always, we start with our base case. The base case is n equals 1 because it says n in the natural numbers. If you did start with n equals 0, I allowed that because some books do have the natural numbers start with 0, and it's true for n equals 0 as well, so that's close enough. Okay. Now when n equals 1, then the limit that we're looking at, x to the n over e to the x, becomes the limit as x goes to infinity of x over e to the x. Hopefully you remember from calculus how to do this problem. It has the form infinity over infinity, and so we apply L'Hopital's rule and take the derivative of both the numerator and the denominator to get the limit of 1 over e to the x, which is 0. Okay, and that's what we wanted. Now we'll go on to our induction. So we will assume that the limit as x goes to infinity of x to the k over e to the x equals 0 for some k greater than or equal to 1, and I'll label that IH for inductive hypothesis. Then, when we look at x to the k plus 1 over e to the x, it still has the form infinity over infinity, which means that we can use L'Hopital's rule again. We can again use L'Hopital's rule, and we get the limit. When we take the derivative of the numerator, we bring down the exponent, k plus 1, times x to the k, the exponent goes down by 1, and in the denominator, the derivative of e to the x is e to the x. Now, can we separate the k plus 1 from the rest of the limit? Can I bring that k plus 1 out in front, or can I separate it into two possible limits? Sometimes we can, sometimes we can't. Remember that this limit is the limit as x goes to infinity. So the variable for this limit is x. That means that k plus 1, as far as this limit is concerned, k plus 1 is a constant. So because it's a constant, I can bring that k plus 1 out in front, like so. And so now I have a constant times, now this limit, this is exactly what I have in my inductive hypothesis. So this limit is 0. A constant times 0 is 0. And that's precisely what we wanted, and so we can say, therefore, by induction, thus this limit equals 0 for all natural numbers n. Last, I want to talk about the problem about the Fibonacci numbers from your homework. So the problem looked like this. Prove that f sub n plus 1 times f sub n minus 1 minus f sub n squared is equal to negative 1 to the n for n greater than or equal to 2. And f sub n, that's our notation for the Fibonacci numbers. So again, let's start off with a little bit of scratch paper work. First of all, I like to put the table with the Fibonacci numbers over somewhere on the side or the top of my page or something like that, because it just helps me to have them all there for reference. Okay, now let's try just checking a few values. So we'll try when n is 2, I get 1, when n is 3, I get negative 1, and when n is 4, I get positive 1. So that all looks pretty good. That's interesting. Now let's think about the induction step. So for the induction step, the first thing we want to think about is what is the inductive hypothesis? Well, the inductive hypothesis would be that the statement we're trying to prove basically for n, or you could put k, whatever you want. Now I want to look at this statement with n plus 1 subbed in for n, so I'm going to look at the left-hand side of it. It looks like fn plus 2 times fn minus fn plus 1 squared, and I want to show, WTS stands for want to show, negative 1 to the n plus 1. Okay, well, when I first tried this problem, let me show you what I did. I thought, well, we have the formula for the Fibonacci numbers, and so we can use that formula to expand each of these terms. So the first term gets expanded, the second term, and then plus, whoops, that should have been a minus. But either way, I looked at that and I thought, okay, so I'm going to have to FOIL the first part and then FOIL the second part, and it really quickly just kind of went bad, and I thought, okay, that's not what I want. So let's back up. Now, a very good strategy with the Fibonacci numbers is to be selective about when you apply the Fibonacci formula. So let's just apply it to the term with the highest index, so the term with the n plus 2. So we'll just apply it to that one. So we'll write that first term as the sum of the two previous, and then the rest just copied over the same. Okay, a little simplifying, we'll distribute the f sub n. Alright, and now from here we might notice we have an f sub n squared, and that term occurs up here in the inductive hypothesis. So if I take that inductive hypothesis and I solve for f sub n, little algebra, and I get that. Okay? So let's try substituting that and see what happens. So we substitute for that, this big messy formula. And if I look at the first two terms now, I see that I can factor out an f sub n plus 1. So I'll factor that out. Okay. And the thing inside parentheses there, that's f sub n plus 1, because that's two consecutive Fibonacci terms. So I end up getting two terms that canceled out, minus negative 1 to the n. So that's minus negative 1 to the n. That means negative 1 to the 1 times negative 1 to the n, which is negative 1 to the n plus 1. Yay! Okay, so now I think I've got it. It all worked out, so I'm going to go ahead and write up my proof. Okay, proof by induction. For the base case, let's let n equal 2, and then I'll look at the formula and notice that it equals negative 1 squared, which is what I wanted. Okay, now as an inductive hypothesis, assume, you always want to assume your inductive hypothesis. You want to have the word assume or suppose in there. Okay, now we know we're going to use this identity where we solved for f sub n, and so just like on the previous problem, it makes sense to kind of prime that, to sort of say like, okay, well I know I'm going to be substituting later fn squared, so let's just go ahead and mention it now. And in fact, I'll even name it. I'll name it star. Okay, and now I can just basically follow my scratch paper work. I expand the first term, distribute the f sub n, apply property star, okay, factor out an f sub n plus 1, and combine the minus signs. And then I'll notice that everything cancels out, and it all turned out exactly the way I wanted it. Okay, thus the result is shown for all n greater than or equal to 2 by induction.